Okay, in this video we're going to study the wave equation. So let's start by assuming that we have a wave that is represented mathematically by some function that depends on both the position and the time. As you can see here, it's a function of x and t. So we know from the previous lecture that phi of xt can be represented as a generic function of x plus minus vt, where v is the velocity of the wave. And also we know that x plus vt represents a wave that travels to the left, and x minus vt, so x plus vt represents a wave that travels to the left, and x minus vt represents a wave that travels to the right. So what we are going to propose without proof in this class is that this function here satisfies this differential equation. The partial derivative of 5 with respect to x squared is equal to 1 over the velocity squared partial derivative of 5 with respect to t squared. This is called the wave equation, and any waves, any type of waves, means if any type of wave, sound waves, ripples in the water, electromagnetic wave, they obey this type of equation. What we want to do now is prove that a function f(x) plus minus vt is a solution of the wave equation. Okay, to do that, to prove that this function is a solution of this equation, then let's define the variable u, which is equal to x plus minus vt, and then we know that partial u with respect to x is equal to 1, and partial u with respect to t is equal to plus minus v. Okay, so that's what we need to do. So now let's work the derivatives one at a time. Let's start with partial of f with respect to x, and this is x plus minus vt. And what is this? Well, this is partial of f of u with respect to x with u, partial u with respect to x, and this quantity here is 1, so this is just partial f of u with respect to u. Let's try the second derivative, which is partial with respect to x of partial of f plus minus vt with respect to x, and this is equal to partial with respect to x of partial f of u with respect to u, simply because we proved that this here is equal to this, so this is equal to this here, and this is equal to partial with respect to u, partial f of u with respect to u here, and then partial u with respect to x, which is just partial of f of u with respect to u squared. Okay, so I have these derivatives on this side. Now let's work out the time derivatives. So I have partial with respect to t of f of x plus minus vt, and that is equal to partial of f of u with respect to u, partial u with respect to t, and that is equal to plus minus v partial f of u with respect to u. So now we're going to work out the second derivative, which is partial with respect to t of partial of f of x plus minus vt with respect to t, and that is equal to partial with respect to t of plus minus v partial f of u with respect to u, and this is equal to partial with respect to u, and then plus minus v partial f of u with respect to u, partial u with respect to t. So this here is going to give me a plus minus v, which this gives me a v squared. So this is just v squared partial second of f of u with respect to u squared. And basically this is proof, because then remember the wave equation was written as partial of f with respect to x squared is equal to 1 over b squared partial f with respect to t squared. And this 1 over b squared cancel this, and I get that this is equal to this. And that is just my proof. Okay, so the last thing I want to do in this video is to see how the wave equation arises in a simple problem. And this is the problem of a wave and a string. So imagine that I have a string. This is a string, say like a guitar string. And then there's going to be vibrations in the string, and the string is going to vibrate, right? So, and we want to write an equation and see what kind of equation of motion is good for this string. So for that, let's look at a little segment of the string. Then we're going to look at a segment, and this is my y, and this is my x. And then here I have a segment of the string, and then this string have a tension pulling up this way, and another tension pulling down this way. Now these tensions are equal in magnitude but not in directions. So I'm going to have angles here, and I'm going to call this theta 2, and this one here I'm going to call theta 1. Now, by Newton's second law, we know that in the y direction, right, in this direction, then we know that delta F in the y direction, which is the force pulling up minus the force pulling down, that is equal to mass times acceleration. So delta Fy is equal to, what is the mass? Let's say has a density, rho, and this distance here is dx. This distance here is dx, as I said. And so, and this length here is ds. So then therefore this is rho ds is just the mass in this length here times the acceleration, which is what? Partial the second derivative of y with respect to time. So now I'm going to write the forces as minus tau, the tension, sine of theta 1 plus tau sine of theta 2, that is equal to rho s, sorry, ds, partial derivative of y with respect to t squared. And then if we assume that the angles are small, then I can rewrite this as minus tau tangent of theta 1 plus tau tangent of theta 2, and that is equal to rho ds partial secant of y with respect to t squared. And now I can write this as dy dx, right? So this is minus tau, then this is partial y with respect to x, that is the tangent here, and this is evaluated at a point x, plus tau partial y with respect to x at x plus dx, which is this point. And then this is equal to what? This is equal to rho ds partial second of y with respect to t squared. And now this is just the second derivative of y with respect to x squared. So this is just tau second derivative of y with respect to x squared, and which is equal to rho ds